record? Yes, here. So welcome everybody. We're having this series of seminars at the Physics Department of the University of Chile, and today we have Andrea Gambassi. He's professor at CISA in Trieste in Italy, and he accepted to give us this seminar on the Casimir, the classical or thermal Casimir effect in this very late hour for him. He's late at night there. Andrea is an expert on critical phenomena and the Casimir effect in particular, and with colleagues, they were the first to measure this effect in 2008. And Andrea make his PhD in Italy in the Scuola Normale Superiore, and then he moved for a postdoc in the Max Planck Institute in Germany, and then he returned to CISA, precisely where he's working now, and he's now full professor since 2 years already. And as I told you, he's going to talk about this thermal Casimir effect. So please, Andrea.
Okay, so thank you very much. First of all, I would like to thank Rodrigo for his kind invitation to give this talk from remote. And when I mean remote, I really mean it, because I'm here in this upper corner of Italy, almost at the border with Slovenia, actually at the border with Slovenia, while you are down here. So you see the distance is a lot. And what I would like to do is simply what I would like to do is to provide an overview of what it has been done in essentially the past 20 years concerning the study of the universal force which emerges when you confine in space critical fluctuations. That is the so-called critical Casimir effect. And I hope that by the end of the talk, I will have convinced you that it is a very promising force to be used in soft matter. So as this is talk is meant to be quite general, I will start by recalling what is the probably best known Casimir effect originally predicted in quantum electrodynamics. Then I will tell you how this Casimir effect in quantum electrodynamics has an analog in statistical physics, with an additional, an important feature, I will emphasize it, that is universality, typical of critical phenomena. And then I will tell you how this effect was originally measured indirectly and then directly in the lab. And then I will tell you what has happened in the past years about applications in soft matter, where for the purpose of this talk, soft matter are essential colloidal dispersion, which means particle can be polystyrene, silica, of the order of micrometers dispersed in a fluid, which can be water or whatever, whatever you like. Okay? Let me start with the Casimir effect in quantum electrodynamics. So in 1948, Hendrik Casimir discovered that if you take two parallel plates perfectly conducting, two parallel metallic plates perfectly conducting, uncharged, and you put them in the vacuum at 0 temperature, they attract each other. It was sort of significant breakthrough, because everybody was thinking that the vacuum is vacuum. So if you put the two things in vacuum, nothing happens. But these were also the early days of quantum electrodynamics. And so people were starting thinking of the quantum electrodynamic vacuum in a different way. So as something which is in which charges and fields are fluctuating freely. Okay, so this is the well-known. And nowadays, nowadays also Casimir, how can we understand the emergence of this effect? This effect is simply, this effect in quantum electrodynamics is given by the fluctuations, or the 0-point fluctuation of the quantum electrodynamics vacuum, and is essentially due to the imbalance between the pressure exerted by the vacuum fluctuation outside the two conducting plates and the pressure which is inserted from inside, because inside the two parallel plates, the electromagnetic field, the quantum electromagnetic field E and B, they have to satisfy boundary conditions prescribed by standard electrodynamics. This means that their wave vector are quantized according to the usual quantization rule. And accordingly, if you study the energy of the fluctuation modes allowed within the cavity, if you want, these are given by the sum of the 0-point energy of the harmonic oscillator, because after all, the electromagnetic field E and B in QED are nothing but harmonic oscillators. So the 1/2 h bar omega is the sum of this 0-point energy over all allowed modes, and the allowed modes are quantized according to this law. This means that this energy E depends on the system of the thickness of the cavity. And then this means, and then one discovers that if the distance between the two surfaces is much larger than some microscopic scale, eventually the radiation, the vacuum fluctuation, exert a pressure, a force per unit area, which is given by a universal constant, and then by the only dimension, the only dimensionally correct quantity that you can construct from h bar, C, and the system's and the cavity size to get a pressure. Okay, so this expression tells us that it's a quantum phenomenon, electrodynamical, because there is C, and then L to the 4 comes out of dimensional analysis. Okay? So this was a striking prediction at the time. As I said, these were the early days of quantum electrodynamics and the idea that something can occur in a vacuum. And here you can see a cartoon of it, essentially. Whenever you have a fluctuating field which is constrained by boundary conditions, because of this imbalance of the forces, you see that you generate, I can show it again, no, sorry, I cannot show it again, can generate a pressure, you generate a pressure which makes the boundary moving. So here is even a classical effect, you can even do it with. And clearly in this quantum electrodynamics effect, the sorts of fluctuations which make in this analogy this string vibrating are the fluctuations, the quantum fluctuation of the vacuum. Okay? So after this prediction, they attempted immediately some experimental measurement in 1958, but then the first convincing experimental evidences of this came only much later in 1997, 2002 by using atomic force microscopy. And so this took quite a while, okay, to verify experimentally. Actually, there are still some things which have to be understood also in this context, but this goes beyond my talk. So, but in 1978, Michael Fisher and Pierre-Gilles in this memory to the Academy of Science of Paris, they pointed out that something similar to the Casimir effect of quantum electrodynamics should occur also in statistical physics. And in these notes, they were talking about, so the title of the note is Phenomena Occurring at the walls immersed in a binary liquid mixture. Okay? So they were talking about fluids, binary liquid mixtures, so liquid mixtures, and things that happen when you insert in this liquid a wall, okay, or a solid substrate. This was essentially the beginning of this Casimir-like effect in statistical physics. But in order to show you how comes that you have an equivalent of the Casimir effect in statistical physics, let me tell you first, let me briefly recall you what is a binary mixture, what happens when you plug into it a wall, and give you the various elements to understand what's going on. So, for example, let me start by recalling the phase diagram of a binary liquid mixture. Imagine you have two substances A and B, and then the phase diagram is simply expressed in terms of the relative concentration of one of the two components, let's say A, and the temperature. It might be that these substances are such that they are, if you prepare them with a certain relative concentration in a test tube, and you prepare them at a certain temperature T here, it might be that they simply demixed into an A-rich component and to a B-rich component here, and there is maybe an interface between them. Okay? And so It might also be that, it could be that this depends on the mixture. Clearly, it could be that upon approaching the upon increasing the temperature, then the substance will eventually become at high temperature completely homogeneous. So you can no longer distinguish the two components A and B, the two liquid components. And in order to distinguish this case from this case, it's very convenient to introduce what a quantity which is fundamental in all the discussions. It is the order parameter. The order parameter, which is a measure of the local concentration of one of the two components with respect to a reference value. Okay, so clearly in this condition here, the order parameter is spatially homogeneous because concentration of A is essentially constant apart from gravity effects within this test tube, while here clearly the concentration of A will be larger here and smaller here. So the order parameter is something which allows you to distinguish a disordered configuration from an ordered one. And so in this line of the mixing transition, as it's well known, it ends up in a critical point. And when you prepare the substance in the test tube at a critical concentration and you raise the temperature, you can hit the tip of this curve, which is the critical point, characterized by the emergence of the critical opalescence that you can see here. You see this whitish region here. Critical opalescence is telling you that the order parameter fluctuations, which are of thermal origin, becomes correlated in space at a length scale which is able to scatter light. So it means that quite in general, the order parameter correlations will be correlated in space across the so-called correlation length, but this correlation length formally diverges when you approach the critical point. So in principle, you get correlation over all scales. And as you know, this idea that you have order parameter fluctuations which are correlated along all scales is essentially the basis of the idea of universality put forward by Landau. Universality, as I said, is going to play a fundamental role. It's going to be a leitmotif of this talk. And it is important in theory, it is also important in practice, as we see. In theory, why it is important? Because it tells us that systems which are microscopically completely different, for example, a binary mixture or an easy model on a lattice, in spite of the fact that they are completely different, as long as they share the same symmetry conservation laws and so on and so forth, they will eventually display the same kind of collective behavior, because what happens at the mesoscopic scale set by the correlation length is rather insensitive to the macroscopic scale. This means, for example, that if instead of studying the binary mixture, we study, for example, this lattice gas on a square lattice, which we have particles A and B, and we study it at low temperature, we can measure the correlation length, for example, by Monte Carlo simulation. And when we increase the temperature, we will observe that these two regions, which are clearly distinguishable as it is here, they start to be the fluctuations will start to increase. The correlation length also will start to increase till you hit the critical point. The system becomes disordered, and eventually you will end up. The correlation length decreases again. You will end up with a homogeneous phase, which it resembles a lot to what happens here. And if you do this simulation, you measure the correlation length. When you fit it, you will discover that it diverges with the same exponent as what you expect to see in the binary mixture. So that's a case of universality at play. Now, what is important here, critical point, you have strong fluctuations of the order parameter, which are fueled, if you want, by thermal energy. Okay? Now the analogy, and then I have to tell you what happens when you add a wall into this fluid. Imagine now you have a fluid in which the order parameter is positive, so is reaching component A, so and it will fluctuate in space because of thermal fluctuation. When you add a wall, three things might happen. For example, it might be that this wall that you add likes the A component, so the order parameter will try to be enriched at the wall. It might be that the wall doesn't like particularly the component A, so it will be depressed towards essentially making this order parameter vanishing at the wall. Or it might be even that the wall prefers the other component, no, the B component, in which case the order parameter will be strongly depleted, and the area around the wall will be particularly rich in air. So these are essentially the three kinds of boundary conditions that a wall might impose on the order parameter of the phase transition. And these are usually referred like plus, because this is equivalent of having morally a magnetic field. If we imagine that phi represents a sort of magnetization pointing up, this one corresponds to having the order parameter field vanishing at the wall, so like the Dirichlet boundary conditions. This is minus, indicating that you have a field which penalizes the order parameter, and you have absorption of the other component. Okay, so these are the effects of a wall. So essentially, having a wall amounts at imposing boundary conditions to the fluctuations of the order parameter. Now the reason why we have a Casimir effect of the theory of physics should be clear, because if we think of what happens in QED, we have a fluctuating quantity, which are the electromagnetic field of quantum origin. The excitation are of quantum origin at t equals 0, and the range of fluctuations is infinite because the photon is massless. When you confine these fluctuations by imposing boundary conditions, the field, you discover that you have long-range forces. Now in statistical physics, you have a fluctuating quantity, which is the order parameter of the phase transition, irrespective of the kind of phase transition that you have. You have fluctuations which are excited thermally. You have a correlation length which is finite, but this correlation length, we know that it diverges at the critical point. And now it's not surprising that when you confine, you will have a force acting on the confining wall whose range is set by the correlation length and becomes long range at the critical point. Okay? So then when we do the comparison, this is what I told you before. Now, when we consider here in statistical physics, we can confine whatever medium. It could be helium-4, a binary mixture, a liquid crystal, it could be a Bose gas, whatever is able to sustain a second-order phase transition. And so what we expect is that the force, which actually we will see can also be repulsive, while in QED is typically attractive, it has a finite range. But when the correlation length of the fluctuations and the size of the system are sufficiently large compared to the microscopic scale, what turns out is that the pressure exerted on the wall, on one of these surfaces, turns out to be sort of universal, as it was in the Casimir QED, in the sense that it depends on the dimensional full combination of KBT divided L to the cube, which gives you the dimensionality of a pressure, times not a constant, not a universal constant, but a universal function of the ratio between the distance between the two walls and the correlation length. And this function here is universal in the sense of critical phenomena. So it depends only on the universality class of the phase transitions occurring within the medium. And in addition, it depends also, still in a universal way, on the kind of boundary conditions that the two walls are imposing on the order parameters. So these are the only ingredients that you need. And this universality is fundamental because this allows us to do the experiment in the lab, then do the simulation, the calculation theoretical in an equivalent model, in a model which is in the same universality class as the actual system that you study in the experiment. And then the comparison should be essentially an almost parameter-free comparison, or a comparison with very few parameters, in which very few material properties of the system enter. Okay, so that's the power of all this. So when you start wondering how large it is force, you check that the one in QED for 1 centimeter square at 1 micron is 10 to minus 7, which is very small. But if you look at the critical one at room temperature, is even smaller. Okay, so you see it's a significantly small force. And now the question is, how can you measure it? So the first indirect measurements were done so first of all, the problem is to realize a micrometer film, or liquid film, confine a liquid within a micrometer layer. What you can do, you can exploit wettings. That is, you prepare, you take a liquid, you prepare it in the vapor phase, but very close to the gas-liquid transition in the phase diagram. So it might be that if you expose this vapor to a solid substrate, the interaction with the solid substrate with the vapor is able to provide you this small extra pressure, which allows you to condense what the so-called wetting layer on the substrate. So in this way, you create naturally a liquid film with a certain thickness L that can be controlled, and in some cases, in the case of complete wetting, the thickness of this film can be controlled, and it actually diverges when you get when you tune the pressure towards the liquid phase. Okay, so you have a possibility to create a film of a certain thickness. Now, for example, if you have a way of controlling the thermodynamic parameter in such a way to go along this line, you can monitor the thickness of your film as a function of temperature. It will stay constant, for example, something of the order of nanometers. Now, if you are able to realize a liquid-liquid phase transition within the liquid film, then the fluctuations of the order parameter will be confined within the film, will exert an extra force on the vapor-liquid interface, which essentially will be you expect it will be displaced. Okay? So, for example, this means that if you take a fluid which has a liquid-liquid phase transition of second order, which ends at the critical end point, and you go along the same path as before, when you pass close to the critical end point, the fluctuations within the liquid due to the being close to the critical end point will create a force which will displace the interface, and you will see a dip like this. So that was the first ingenious way of measuring the force, so this effect, okay? So what is the best fluid with a liquid-liquid phase transition is indeed the helium. You have the normal superfluid transition. So if you are able to prepare a wetting film and go along this path in the phase diagram, you should be able to see that this wetting film shrinks, okay? So now the question is, from the theoretical point of view, we know that the normal to superfluid transition helium-4 belong to the XY universality class. So what you can say, okay, now XY universality class means that in practice, if I want to do quantitative prediction for this phenomenon, I can simulate the XY model as classical spin model on a lattice, and then I have only to understand which boundary condition I have to impose in my film of XY model. And it turns out that they are naturally the Dirichlet boundary condition, because the order parameter in the helium is the wave function which vanishes in the substrate and the vapor. Okay, so then you do your Monte Carlo simulations. This is something that we did long ago, and you discover that you can calculate this scaling function theta, which is the quantity the pressure depends on as a function of this variable x, which is nothing essentially the tail over xi. You discover that it's attractive. Okay? And when you do the experiment, and the experiment was something very finely done, because the signal in the experiment is essentially in this dip, which is zoomed here. When you do the comparison with the experiment, you see that the agreement is striking. You know, this is almost a parameter-free comparison, okay? And is attractive. So this was a very big success. Then you can change in order to make this, given that the force is proportional to kBT, if you increase the temperature, remember the helium T is of the order of few Kelvin. If you go at the high temperature, you can consider the same phenomenon, but in which the liquid undergoes the mixing transition as the one we discussed. And then in that case, as we said, we can have also plus and plus minus boundary condition. It might be that the solid liquid and the liquid vapor interface, they prefer the same component, and this would be plus component A, or the opposite components of the mixture. And then if you want to do prediction, you go you do the simulation on the easy model, which is the one which represents the liquid. And then you discover that if the boundary conditions are the same, the force is again attractive. It has this property, the scaling function. While here, the scaling function, if the boundary conditions are different, the force turns out to be positive, that is repulsive. And also in this case, the experiment were confirming quite nicely the theoretical predictions. Okay? So this was the situation. But then, you know, these were films, and so preparing these films is highly non-trivial. But then if you believe that there is this force, as I showed you, also experimental force acting on films, if you imagine that you make this surface here slightly curved, it's not surprisingly that a same force will also act between a flat substrate and a colloid, in a sphere. And in particular, actually, if you assume that the radius of your colloid is much larger than the separation, you discover that the force takes also this universal form where this scaling function here can be derived by the so-called diagonal approximation or proximity force approximation from the same scaling function derived for two parallel plates, okay? So in principle, we have, once we know this theta parallel, we have a prediction also for this scaling function here for a surface and the wall, okay? Armed with this, then the idea is to see what is the effect, how can we measure this force directly on sphere, on colloidal particle. And the scale of the force is kBt, that is the typical scale of energy at which the physics of soft matter occurs. Okay? So, but we needed a sufficiently fine dynamometer, and the best dynamometer that we have is the so-called total internal reflection microscopy, which performs much better than AFM and even by the pioneering experiment by Cavendish on gravity. So the internal reflection microscopy consists in the fact that you take a laser, you shine it on a fluid sample at an angle which is larger than the total reflection angle, and therefore the laser does not penetrate the fluid, does not propagate in the fluid, but you have a penetration of an evanescent field. And when you have a colloidal particle placed in an evanescent field, this colloidal particle blinks with a blinking intensity which is proportional to the intensity of the evanescent field. So if you record the intensity and you know how the evanescent field depends on the separation, then you can essentially monitor the distance between the place of total internal reflection and the position of the colloid. So what you do is an experiment like this. You observe the blinking of the colloid. Essentially what you are doing, you are monitoring the Brownian motion of this colloid in the fluid, okay? So you can record the intensity. From the recording of the intensity, you can extract the statistics of the intensity, knowing the relationship between the intensity and the distance z, the surface to surface distance z. You can calculate the probability of the z, and given that you are in equilibrium, you know that this probability is to be given by the potential of all the forces acting on your colloid. So therefore, this means that you can extract from the counts essentially the interaction potential between this colloid and the glass, in which the glass prism of the surface of the sample cell, which your system was doing. Okay, so this means that if by tuning the properties of the liquid around the colloid, you can switch on these critical Casimir forces, these critical Casimir forces should appear in the potential that you infer from this experiment. Okay, is that clear? So, yes.
I have a question. Just what you show,
yes,
that you are sampling the temporal evolution of this colloid, yes?
Yes.
But the Casimir force is this critical Casimir force. It does not show also this critical slowing down. So
yes, but
I don't know if you are sampling the potential or something retarded or
no. As long as you are in equilibrium, this means that if now the question is, if you are really too close to criticality, the equilibration time is going to be too long. But nonetheless, as long as you start to specify detail balance, you are in equilibrium. When you collect all the data, then you know that the statistics is given by the force. So the dynamical aspect is washed out in a sense. Okay.
okay.
Andrea, also I have a question. So
Yes.
what happened about to the roughness of the wall? Because if you have some roughness, maybe also you can induce some effect, fluctuations.
No, this one not really. I mean, this is not. I mean, this clearly is a tremendous problem when you want to measure the Casimir effect in quantum electrodynamics. But here, the roughness clearly, as long as it is at the scale smaller than. So here we are talking about micrometer size colloids. So if you have roughness which is less than nanometer, then there is absolutely no problem. Okay. And so this typically does not influence, is not expected to influence the measurement. Okay?
Okay.
So, and this is essentially the setup with which in 2008 we did the first measurement of these Casimir forces, in which the binary liquid mixture was water and lutein, which is characterized by the phase diagram. So it has a lower critical point convenient temperature, but these are experimental details. And what we measured was having, I show you here, what we measured was that we consider an hydrophilic colloid in front of an hydrophilic surface. And what we observe is that far away from the critical point, we have electrostatic repulsion and then essentially nothing after subtracting gravity. And then you see when you get closer to the critical point of the demixing of the medium, which is around the colloid, an increasingly strong attractive components appear, okay? And these, the solid lines are the theoretical prediction based on the Monte Carlo simulations I showed you before, and you see that the agreement is striking. And the force is of the order of 600 Newtons. But if you change the colloid from be hydrophilic to be hydrophobic, then you change the boundary condition for plus plus, you go towards plus minus, you expect repulsion, and this is indeed what you observe. So far from criticality, you have electrostatic repulsion and then nothing, but then you see that upon approaching criticality, you get curves with increasingly strong repulsion. So we have a repulsive and an attractive force. And everything depends only on the surface properties of the colloid. So we have a temperature control, reversible also. I didn't show you, but you can, if you reduce the temperature, you can see this curve shifting back. Sizable force, and everything depends on the surface. So that's essentially the perfect thing to be applied in soft matter, okay? So this was, as we said, in 2008. This year, there has been another confirmation of the phenomenon, and also a nice confirmation of universality, in which the experiment has been done by taking a non-ionic surfactant, which is a much more complex molecule, in the presence of water. And this non-ionic surfactant, they form micelles, and when the temperature increases, they form worm-like micelles, which have a sizable effect. Remember that the lutein is the typical, the molecule we used, water and lutein, the lutein is the typical dimension of a few angstrom, I mean, it's not huge. While here, we are looking at the criticality of a mixture which involves objects which are 2 nanometers of diameter, but they might be as long as 500 nanometers, so it's a completely different scale. And the mixture of water and these micelles, it is characterized by a phase diagram with a lower critical point here. So here is the mixed phase, and here is the homogeneous phase, and they form this kind of tangled networks of micelles. And what is nice is that they repeated the experiment in total internal reflection microscopy. You can see that again here, you see that there is some interaction, far from critical interaction at short distance, which is not simply now electrostatic as it was in the case of colloid, and then nothing, and then you see that as before, you get this increasing attracting Casimir force, and also here when you extract this part here, which is not influenced by the potential short distances, which is related to the structure of the micelles and so on, which is highly non-universal, you see that the part which you expect to be universal indeed again agrees perfectly with the theoretical prediction that I showed you also. Okay, so this was a nice confirmation of universality that came indeed came this year. Okay, so this going from films to colloids has been a turning point in this whole business of critical Casimir. So indeed, if you check how much times the word critical Casimir was cited in Web of Science, this is its evolution in time from 1998 to 2018. And you can see that there was a sharp transition when we were able to show that you can use this effect in soft matter. Okay. And then, since then, the things that have been done are many. So, for example, you can start saying, what happens if instead of a single, what happens if I have, instead of a homogeneous substrate, I have a substrate which has alternating preferential absorption for the two components of the mixture, and I let a colloid floating on it here, for example. Imagine I have something colloid which is a preferential absorption, a strip with the same preferential absorption, and neighboring strips with different preferential absorption. Clearly, this guy when the Casimir effect is at play, will try to sit on this strip and will try to avoid the others. So you can localize, for example, here, these are taken with the camera from above. This is the Brownian motion of a particle which tends to stay on the strip with the same preferential absorption while avoid the others. And then you can, and clearly if the temperature is small, if the correlation length is very small, the colloid will see the substrate as homogeneous, while this difference is increased when the correlation length increases, okay? And so you can control essentially the spatial distribution of colloids. You can even realize a perfect levitation of the colloid only due to critical Casimir force by exploiting this particular pattern. So you can make colloid levitating on top of a pattern substrate. You can see what happens when you have you can make sort of colloids migrating along a substrate depending on they go and look for the preferential absorption. People have studied the case, what happens when you have surfaces which have a disordered preferential absorption. So sometimes some places prefer component A, some places prefer component B, or the cases in which the preferential absorption on that surface is not fully developed. You can start, study spherical colloids, and therefore you have torques. I mean, many things have been done. You can study what they call a Casimir compass. So cylindrical colloids in front of homogeneous and non-homogeneous substrate which tend to orient, and many other things have been done, okay? So now and then there are surprises. For example, I will mention, Rodrigo, how am I doing with the time?
Yeah, it's okay. I don't know.
Okay.
10 more minutes.
Okay, so I'll try to speed up because there are many things I would like to say, but as usual. So sometimes there are also surprises. For example, in this case here, what happens? The question was, what happens if you take a colloid surrounded by the binary mixture, which has a different preferential absorption as the substrate? So you expect a repulsive critical Casimir force. You expect a repulsive electrostatic force between the two. Then what happens if you add a salt to the liquid around? Well, you expect that because of the salt, the electrostatic force will be screened, so it will decay faster. But then anyhow, you have at play here two forces which are both repulsive. And then you expect that the overall force when I measure it will be repulsive. What happens instead is that if you are far from criticality, you have electrostatics and then nothing. But then when you approach criticality, first you develop an attractive force. And then when you get closer to the critical temperature, you move towards these curves and eventually you will have repulsion. So strangely enough, by summing two repulsive forces, you get on the way to criticality even attractive potential. So this was a puzzle that we managed to solve, and this clearly tell you there's a non-trivial interplay. Then the question was, okay, this is what happens with a single colloid, but when you start having many colloids, you expect that this critical Casimir force is another effective interaction temperature control and can drive, for example, the aggregation of colloid. And actually, this was one of the original motivation for studying critical Casimir force. So this has been studied in detail in the group of Dietrich. And this means that you have to do also theoretical prediction for what happens for two more colloids and so on and so forth. And actually, this experiment with colloids even managed to take the critical Casimir effect on board of this International Space Station. There have been a certain number of experiments on critical Casimir forces done in microgravity. Then more recently, in recent years, there have been even a US patent about using, so this was 2018, about using, so here we propose a conclusive demonstrate the effectiveness of a size selective particle purification separation method based on Casimir forces. So Casimir forces has been used for the proof of concept, to prove that you can separate in a selective way particles of different sizes. And I mean, this is a collective behavior. More recently, this was actually this year, for example, they also show that you can use critical Casimir forces as an in a colloidal dispersion to control the deposition of nanoparticles on a substrate, okay? And this seemingly this is a challenge in nanoscience, and by using these critical Casimir forces, they managed to do it. I mean, this was especially in the group of Peter Schall. I don't give you details. Now there are also things that are now addressed. I mean, these are papers of last year. The problem of patchy colloids, so colloids which have they were non-homogeneous, but they have preferential absorption for one kind on a part, and is for the other component. And then what you can observe, these are can observe, for example, experimentally. So the force, the effective force between the two colloids depends clearly on the orientation between the patchy particle, and then they can even create structures. So here you are far from criticality, but when you get close to criticality, and therefore the Casimir force starts playing a role, you see that even you can form these kind of strings, of colloidal strings. Okay, these are experiments. I think I have no time, but I'm
Oh, yes,
sure.
yes, you have a.
Okay.
Okay. I think that you have 10 minutes.
Okay, so I will flash you about the things that we did in the past years, more recently. So what we were wondering, it was clearly, I mean, this critical Casimir force is an effective force. So you expect to have many body effects. So in the sense that if I have two colloids immersed in this near critical medium and I know their interaction potential, when I add a third colloid, it is very unlikely that the interaction energy of the three colloids is simply the pairwise sum of the interaction energy between each pair separately, because there is a full effect. Okay, so the problem of these many body effects, we know that in gravity and electrostatic in vacuum, they have no many body effects. But all effective forces in general, like Casimir QED, depletion forces, Van der Waals forces, and therefore also critical Casimir forces, this equality is not true, but you have to account for full many body effect. Okay. Sometimes this many body effect is neglected for practical purposes, and you can use the diagonal approximation and so on. So there was a theory. The theory, flash it, was a bit. There were several theories about it, mean field theories done in universality class or Monte Carlo simulations for this. But the conclusion were that this many body effect should be there. Sometimes is increasing the energy, sometimes decreasing the energy. It depends strongly on the geometry, on temperature, on the surface property. And it could be up to 25% of the other contribution. It should be a stronger critical point. But the question was, can we see it experimentally? So this was a challenge experiment that I collaborated with the experimental colleagues, and it took us quite a while to do it. And how we did it? We did it in the following way. We started by taking two colloids trapped in an optical trap, and by monitoring the interparticle distance. From the probability distribution function of their interparticle distance, you can infer a sort of effective potential of these two colloids. Clearly, if the correlation length is small, these two guys, they don't see each other because of the critical Casimir force, and therefore when you look at the probability distribution function of this distance, you will see only the effect of the trap, and possibly when they get close enough to feel electrostatics or an electrostatic thing. And when the correlation length increases, while they fluctuate in their traps, they get close enough to feel the Casimir force, and then they will tend to stay there. Okay, so this means that when you calculate this effective potential, you will develop a dip corresponding to when they get close. Okay, so it's here trap, here this dip is due to Casimir force, and then eventually there is electrostatic repulsion. So for two colloids, you know the form of the trap, and in principle we have theoretical predictions, which are the ones that I told you can be inferred from Monte Carlo simulation also for the Casimir part. So we know the trapping potential, optical trapping potential. We know that this potential V2 is just the sum of an electrostatic repulsion, the critical Casimir force, which will become deeper and deeper. Okay, so in principle, by fitting the experimental data that we get with this potential, we can infer all the parameters which are somewhat left free from our theoretical model, that is the correlation length, which you typically don't measure directly, and the parameters, the bioscreening length and the strength of the electrostatics. Okay, so if you do the experiment in two particles, in a sense, you're able to fix completely the two-particle interaction. So the idea then is simple. The idea is to get the third particle close, and again, and you continue monitoring the distance between the two. You do the same experiment. When the correlation length is large enough that the three particles see each other, you will see as before something like this. But in principle, if there are three bodies contribution, you will see something which differs from the previous one in the absence of the third particle. So the third particle is going to influence also the effective distribution of these two guys. So the idea is simply, let's check whether what we see experimentally is compatible with the pairwise approximation for this term here. Okay, I hope this is clear. And so what we do, we assume that we have no many-body interaction. We know all the data, so we can calculate what would be the distribution in the absence of three bodies interaction. And what is the discrepancy with the experiment is telling you that you have a genuine many-body contribution. Okay, so this was the experiment. I don't tell you the details. Is done with digital via the microscope, but essentially you still record the Brownian motion of the colloid. You use still water and lutein. This is exactly what we did. So you get you first measure the two colloids with the third one far away, and then you get the third one close. This is the result. Okay, so this is again the effective potential of the distance between these two particles, with the third one far away. And then you see that it has this shape, and the dots are the experimental data, and the solid line is the best fit to the theoretical prediction, which gives as a result the correlation length. And now here I show you the same condition with the third particle close. And you see that also here, assuming on the right-hand side that you have no three-body interaction, okay? So pairwise approximation, okay? Now you see that when you get close, as I promised, you close to criticality, so you increase the correlation length. You see that it develops sub-deep in the two-body problem. And also here it develops, you see that the experimental data start developing a deep, but you see that the theoretical prediction in the absence of three-body then starts really to depart from the actual experimental data. So here you get closer to criticality, and you see that still you can fit the two-body theory, the two-body problem very well. And here you see that the discrepancies are increasing. So you get closer to criticality, closer and closer, the deep becomes deeper and deeper. But as you can see in this region here, you have clearly discrepancy between the theoretical curve, the solid line, which you expect to see in the absence of three-body forces, and the experimental data. So this is telling you that you have many body effects. So it was what we managed to do. Then there is another chapter that I just flashed because I'm over time. That is the whole issue of dynamics, in which I'm currently also interested in. Okay, so I will tell you just briefly that what we did recently, actually a couple of years ago, was to study the effects, how you can use the Casimir effect to delay the dynamics of two colloids. So have two colloids in the fluctuating medium. So if there is the Casimir force acting between them, they tend to stay close. Clearly, if there are only two colloids, they will eventually diffuse because of entropy, if you want. But in a sense, the Casimir force is breaking them a bit, is keeping them, they tend to stay together. So for example, if you look at the first passage time to a certain distance, this first passage time will decrease, but this is probably, this will require me some more time to explain this. But so my point, let me go to the conclusion. Okay, so this was the, okay, so let me go a second and go to the conclusion. Yeah. So there are actually many perspectives. So my message is many things has been done. This Casimir force can be applied. So there are now, okay, so from the theoretical point of view, clearly there are, for example, these many body effects, they have to be investigated in more detail, and clearly you expect them to be relevant to also for the aggregation of colloids. Many body effects also, the issue of how they depend on the shape of the system is unclear. The effects which go beyond the three bodies. But I was saying, one important chapter which is still largely unexplored is the one of the dynamics of this critical Casimir force. So if there are effects of retardation, how they really influence the aggregation of colloid. And then this is just a teaser to Rodrigo and co-workers, something on which I'm working on. Imagine now that instead of having passive colloids, you have active colloids in correlated media. And this is actually what I'm currently working on. And I should be able to show soon a draft. Or the formation of structure of colloids due to the presence. So we have seen that you can form kind of worms in the presence of patchy particles of the general formation of structure. And then there is this big chapter of applications, practical application, because if you want, after all, what is clear now is that the critical Casimir force is one of the most easily tunable interaction in soft matter. Easily tunable in the sense that by changing the temperature, you can change a lot its range, you can change its sign, in a way which is typically, it's much more difficult to achieve with all the other forces that you can think of in soft matter. Clearly then, here I was always only talking about fluctuations of the parameter, but then the fluctuation can be provided by fluid in the interface, by membrane, by granular media. This is something that Rodrigo and Ricardo investigated many years ago, and there have been also other works trying to go to understand these effective forces in granular media. So there is, I mean, the things that one can explore are really many and can go in different directions, more fundamental or also more applied. With that, I would like to thank all my collaborators in the course of the years. So the various people of the belonging essentially to the group of Professor Dietrich in Stuttgart, with whom we developed the theory. And then also the many experimental colleagues, starting from the group of Clemens Beckinger, which was first in Stuttgart, now is in Constance, and also more recently the experimental group of Giovanni Volpe in Gothenburg. And then I would like to thank you for your attention. These are the credits that I have to show, given that we are recorded. So this is where the material is coming from.
Thank you very much, Andrea. Very interesting your talk. So have plenty of time for questions. I don't know if there are some questions. Marcel Clerc has a question. Yes.
Yeah, so with respect to this effect of non-equilibrium, so I wonder what happened in the case of the colloidal experiment, but you take a thermal gradient. So you can control.
Okay, so that's okay. So this is there is another chapter of this. So when you have a thermal gradient, okay. So now I can give you different answers. So if you have a thermal gradient, this is something that has been studied by Sengers, Ortiz de Zarate, who, by the way, I think passed away. And so you expect to have giant fluctuation-induced forces, okay? So they called it up like this. And there is a series of work by Sengers, Ortiz de Zarate. There have been also experiments, by the way, also going to the space shuttle by a group of space shuttle, International Space Station, by a group of colleagues in Milan. So you observe a very strong effect. On the other hand, if I want to be a purist, then I would tell you that in a sense, if you have a thermal gradient, So imagine the parallel plate. If you have a thermal gradient within your system, it's not surprisingly that you have a huge effect, because you are creating by hand an imbalance between the pressure on this side, While in the Casimir force, there is no imbalance created by hand, okay? So this just comes out of the fluctuation, but there is an effect. Clearly, then you have to disentangle it from other effects which are due to gradients, like, I don't know, thermophoresis, for example, okay? But there is an effect, yes.
Okay, thanks.
You said that this force is highly controllable because you just need to control the temperature.
The temperature, yes.
Yes, but it's in a very small range because you have to be very close to criticality.
Yes,
and
okay, so this is true, but the fact is that keep in mind that essentially, okay, clearly, if you want to think something which is operating at any temperature, then better to think of something different. But if as many actually, as there are many devices which operate at at fixed temperature, okay? So remember that essentially you can find, you have critical points essentially at all temperatures. Okay, so if you tell me, I want to realize a machine which works at 37.2 degrees, I can find almost surely a binary mixture, for example, which has that critical point. But then clearly you have to be to stay stable around that temperature, because if you go out of that temperature, you will lose the force. Okay, this is true. I mean, but you know, for example, as I said, this application, fabrication processes and so on, in which you are able to control the temperature a lot, then it turns out that the possibility of switching on and off this force is very convenient. Okay? So let's say, I mean, clearly, if I have to write a grant, I write that, but I mean, practically, you will never make a machine out of this. But you can use it to control fabrication processes, the position, things in which you can control the temperature. Yes.
Okay, but in this dimensionless temperature, that is T minus Tc divided by Tc, how close you have to be to?
Okay, so that's another issue. Okay, so what is important actually is that the correlation length is much larger than the typical molecular scale. So if you want, now we have also to distinguish two things. Let's say the effect is there even if you are not very close. So, let's say typically, if you are within a tenth of a Kelvin, 0.2 or 0.3 is still fine. When you go at 0.5, you have still an effect. Probably is not going to be universal, so you will start seeing discrepancies compared to the theoretical predictions based on universality. But if you don't care about universality, you care about applications, then that's also fine. And actually, effects of the Casimir effect has been seen even 1.2 degrees out of criticality, especially in these complex micellar systems, in which even 2 degrees far from criticality, you can achieve quite large correlation length on the scale of the colloid, okay? So you have to distinguish whether you are interested in having a good comparison with the theory, then you have to be as close as possible to criticality, or to have a forwards, which maybe is not exactly the same that you can predict on the basis of universality, but the force is still there. Okay?
I see. Okay.
Clearly, if you go 10 degrees, forget about it.
Yeah, sure. So there's a question from Spain, from Ricardo Brito.
Hi. Nice talk, Andrea, as usual.
Thank you. Thank you, Ricardo, for staying awake.
Yeah, well, it's the same time for me as for you, so that's not a problem. But I was wondering, can you design a Casimir ratchet, say in these structures that you have sort of invented with bands, this blue and red, say something, construct a protocol, say with the temperatures in which by raising the temperature above, say, the critical point and lowering close to the critical point, can you sort of induce a directed motion? Because that could be maybe useful for
I can show you
segregation or...
Okay, so let me see if I find it. Okay, let's see. Can you see this? Okay.
Yeah, for instance,
so
that was what inspired.
You see, actually, this is, let me show you. So for example, look at this. In this case, imagine you have this blue colloid that they like to sit on the blue part. Okay. So in this case, and this was done indeed, so blue and red means to be hydrophobic and hydrophilic. So in this experiment by Beckinger, they managed to create a substrate which goes from being hydrophobic to be hydrophilic. So here is red and here is blue. This means that if I put a colloid which is hydrophilic on top of this surface, if the temperature is, if you are far away from criticality, the colloid will simply float homogeneously on top of the substrate. But when you increase the correlation length, so the colloid starts filling the substrate, it will try spontaneously to move on this side, where it is the substrate is hydrophilic as the colloid. Okay, so in this sense, here you can. There is a problem that when they did the experiment here, they were not actually exploiting this fact. So the colloid was kept fixed in position by an optical tweezer. So they measured what was going on here and was measured what was going on here. They didn't let the colloid go. But if you let the colloid go, clearly you can do that. And so,
yeah, but if you go above now the critical temperature, this will make, imagine that you really go above the critical temperature, then they will do a random motion.
Yes.
So it will go to the red. What I mean is that sort of to engineer something that then when you go above the critical temperature, it does a random, but sort of directed. So finally, when you alter these stripes, red, blue, by going up or down or something, they go always to the same direction. It's a bit more complicated. It's not in one of these bricks, but say
probably
many
what you
bricks
can
together.
do, yes, exactly. So if you start putting this tile one after the other, so when you are far from criticality, but then when you get close to criticality, but you have to synchronize, you have to go up and down in temperature in order to be able to have a directed motion, probably.
Yeah, maybe.
Yeah, this is an interesting question to think about. Yes.
I mean, it will be fun and maybe it's useful. So,
thank you. Yes, that's true.
I had another question, but I forgot. Maybe it will come later.
Yeah.
Okay.
I was writing. Thank you.
Thanks. I don't know if there's another question. It seems not. So I will thank Andrea for this very interesting talk. And
thank you all. I mean, if you have if somebody has some curiosity, simply send me a message, and I will be happy to answer to all your questions.
And I remember the question. So
yes,
it's about the experiments of oh, I forgot his name. This Italian. Oh, stupid. Sorry, I forgot the name. Sergio Ciliberto.
Ciliberto, yes.
Yeah. He's doing also some experiments. I mean, I'm asking you about him, but he's also doing some experiments with traps, optical traps.
Yes.
Trying to measure Casimir.
Yes, actually, he did, unfortunately, I mean, while I was about to start the talk, I forgot, I remember that I forgot to mention his experiment. I mean, this experiment was funny because one day I was visiting him in Lyon and I told him what I was doing with this many body. And he was doing exactly the same with two colloids. So what he was doing the following experiment. So he was having two colloids trapped in an optical tweezer. two optical tweezers, exactly as the case in the situation I was using to measure many body forces. And then what he was doing, he started moving one, because you can move the optical tweezer, and then you can check what happens to the other one. So if I move the trap, then the particle follows clearly. But then this other one is in its harmonic potential provided by the optical tweezer. The question is it going to move or not? Clearly, if the correlation length between the two colloids, the correlation length of the fluctuations of the
critical fluid inside
is small. If I move this one doesn't feel anything apart from possible pressure of hydrodynamic origin related to the fact that you're moving a fluid. But what you observe, this is did it very nicely in his experiment. What you observe is that when you increase the correlation length, so the motion of this guy is going to be transferred to this guy. So the second colloid, which is in a fixed trap, it starts moving in a synchronous way with the other. But on the other end, for the kind of motion that it could give to the moving colloid, it turns out that his experimental data were in a adiabatic limit, in the sense that the two colloids, they were interacting with each other in the way, with the force that they would feel if they were in equilibrium at that instantaneous distance. Okay, so he didn't observe what I would term retardation effect, due to the fact that if you move one colloid very fast, the fluctuations of the ordered parameter will take much longer to relax, and therefore the force between two moving colloids at a certain distance is not the same, should not be the same as the force of two resting colloids at the same distance. Okay? And this retardation effect, we investigate them at the mean field level in a paper with Dietrich, but the experiment, they have never been seen. Dietrich and Hajime Tanaka, we did some numerical studies. And now I'm also studying, I'm going back to this issue with some students here, and so I hope to have feeling. So far, nobody has ever observed really the effect of retardation.
That retardation.
Also in the case, in the experiment I was flashing at the very end about controlling the dynamics of colloid by Casimir force, always also our colloid, diffusing colloids were interacting with this, let's say, adiabatic potential.
Okay.
Yeah.
Now retardation is at a much higher level. I understand that it is much more complicated than the normal, as the Casimir. Okay.
But I think that at a certain point we should be able. Yes.
That's optimistic. Nice. Thank you.
Okay. Okay. Thank you very much.
Okay.
Thank you for everybody. Thank you, Andrea, for staying so long.
Next time I will visit. I will visit you directly.
Yes, we hope that.
Next time. I checked that it's 17 hours of fly, so I thought.
Yeah.
Zoom, you see, in this case is very useful. Okay, so thank you all for your attention, and have a nice weekend.
Thank you as well.
Okay, bye. Thank you.
Bye.
I stop recording.
Bye.